Okay, welcome to week 5, part 1. In this lecture, we're going to take a look at iterables and sequences. Now, we already know how to make use of iterables and sequences, and we have an understanding conceptually of what those are. But I want to take a look in this lecture at how you can make your own classes into iterables or sequences. Okay, so basically, conceptually, an iterable is something that you can loop through using a for loop. That basically, it seems kind of trivial, but that basically is the definition of an iterable in Python. If you can loop through it with a for loop, it's an iterable. Now, there are things that support that behavior that are alternative ways of describing whether something is an iterable or not. All right, so let's take a look at how these for loops actually work. A for loop makes use of two methods in the object, the collection object, through which it is iterating. Namely, the iter function, which takes an object as its argument and returns something called an iterator for that object, and that iterator initially is I won't say referring, because that makes it sound like it's directly referring like a reference, but that iterator is initially set up to indicate the first value in the iterable object. Then to obtain that value, and in fact to obtain any next value using that iterator, we use the next function. Okay, so we set up an iterator for an object. That object might be something like a list or a tuple or a set, for example. And what we get back is this iterator that we can hand to the next function, and the next function returns the next value from that object through that iterator for the object. Now, if you try to obtain the next value from an object through its iterator and there aren't any values left, what happens is a stop iteration exception is raised. Okay, so you can keep asking for the next value. Eventually, you'll run out of values to obtain, and this stop iteration exception will occur. Now, we don't see that happen when we use a for loop, because the for loop, the internal mechanisms of the for loop, capture that stop iteration exception and know internally that, oh, okay, that means there aren't any more values to obtain. So here we have a trivial example. M is a list of 3 items. We're using a for loop to step through the items of M. V is the variable containing each of the subsequent values in M, and this just prints out those values, one value per line. So 2, 5, and 1 on separate lines. Internally, the for loop is using iter and next and looking for and capturing and handling the stop iteration exception. So here we have the same list. We've got the variable m being set up to refer to that same, well, not an identical list, but a list with the same items in it. Okay, so m is referring now to a list containing 2, 5, and 1 as its items. And rather than using a for loop, I'm going to call iter on the list object m to get back an iterator. And I'm using the unimaginative name MIT, or M iterator, for that iterator. Now, each time I call next, passing that iterator, what I get back is the next available value from the object M. So I get back a 2 the first time I called next, then I get back a 5, then I get back a 1. If I call next and there are no values remaining, next generates or raises this stop iteration error. And in fact, that will be perpetual. Let me demonstrate this live. Let me pull up a an idle window. Let's see. Okay, I'm gonna skip this part where I'm getting to the directory where I want to be. User. Okay, so now that I've got my idle window set up, let's go ahead and try this interactively so that it you can see rather than read what's going on. So I'm going to say for v in the list m print v, and sure enough that works. Or if I say, all right, m is still referring to that list of values 251. So if I say m iterator gets iter of m, and ask for the next thing that iterator is iterating over, I get the 2, and then I get the 5, and then I get the 1. And if I request a value from next again, from now on, I'm just going to get stop iteration. Okay? There is no more iteration that there are no more values for the next function to be able to give me back at this point. Okay, so we said that an iterable is something that you can loop through with a for loop. An equivalent way of saying that something is an iterable is to say that it provides the iter function and the next function. Internally, within a class that you want to be able to iterate through, these things are actually implemented as so-called dunder methods. That is, underscore underscore iter underscore underscore and underscore underscore next underscore underscore. In the same way that if you want to be able to convert your object to a string, you have to define the method underscore underscore stir underscore underscore, or if you want to be able to compute the length of the object, you define underscore underscore len underscore underscore. So these are two more of these so-called dunder functions. Now, we're going to assume that the iter function and the next function have been defined to work in a way that makes sense, although that's it's up to the implementer of the class to make sure that the iterator function and the next function do something that's reasonable. Now, because when we run out of values, the stop iteration exception is raised, we're going to have to use the try and except mechanism to wait for and deal with that stop iteration exception. Previously, in examples that I've shown, we've used the try and except mechanism in the most trivial way. That is, we have started out with a try block containing statements that we are fearful might fail for some reason. And then if one of those statements does fail and does raise an exception, we used a single except block to deal with any of the possible exceptions that might have occurred inside of the try block. But the try except mechanism can be much more detailed or sophisticated than that. We can have except handle specific exceptions as well as just any old exception. And we just give the name of the particular type of exception, the particular type of exception that we're trying to catch, following the word except and before the colon. In fact, we can have multiple of these except blocks set up to handle multiple specific types of exceptions. We can also have an unlabeled except, which will handle any other kinds of exceptions. And furthermore, we can have a single else at the bottom in the case where no exception occurred. All right, so here's a more detailed example, a more more detailed example, we'll go with that, of a try and except chain. So up here at the top, we have our try block, and in here we have a bunch of statements, and we fear that some of those statements might fail for whatever reason. Now, if one of those statements fails and raises an index error, all right, this is the kind of error that we get if we try to access an item that is out of bounds within something like a list or a tuple, then we can capture that index error and do something about it with these statements following except index error. Another problem that we might encounter would be a type error. Now, that would be the case if we attempted to access a let's say that we attempted to access an item in a list by using a floating point index. All right, so this is a frustrating thing that you will sometimes trip over. Let me pull up my interface here. All right, so if I say, well, I still have m. If I say m sub 0, all is well. If I say m sub minus 1, all is well. If I say m sub 5, I get an index error, okay? If I say m sub 5.0, well, actually, let me say 2.0. All right, although there is an item m sub 2, the index that I specify has to be an integer value. It cannot be a floating point value. And so here I get yelled at that I have a type error because I'm trying to access an item in a list using an invalid type. And then if I want to capture the stop iteration error generated by applying next to an iterator for an object where there's no values left, of course I can set up the exception for that. If there are even other exceptions that might occur, but I'm not sure which ones might occur, I can have an unlabeled except in my chain of except clauses. And finally, at the bottom here, I can use else to handle the situation where no exception did occur. Okay? So we will try to do some statements. If something goes wrong, one of the exceptions will trigger, and we'll handle the exception in some way. Otherwise, if no exception occurred, we'll do whatever statements are contained within the else. So let's see how this applies to messing around with creating an iterable. Okay. Oh, we need to know one more little tidbit of of behavior in Python before we get to using itera next. We also need to know about the break statement. Now, the break statement inside of a loop will cause that loop to terminate early, and you will simply drop out to whatever statement follows the loop. Here I'm demonstrating that with a for loop, but I can also use break within a while loop as well. So I'm saying for v in this list of values, 32915, print the current value of v. If the value of v is greater than 5, break, and that means that we will not continue on looping through the remaining items in the list if we encounter an item whose value is greater than 5. Well, in fact, we do encounter the item 9, all right? So we print the 9, and because 9 is greater than 5, we break, and we get out and don't continue looping through for the 1 and the 5. Okay, so let's take a look at how we can use while rather than using for as a way of stepping through some iterable object. This is going to look kind of silly because using while is much more complicated. But what I'm really trying to do here is to illustrate what the for loop is doing behind the scenes. So by showing you the equivalent while loop, I'm really showing you how the for loop is actually implemented. Okay, so here is basically what the for loop is doing under the covers. When you use a for loop, what happens is that an iterator gets created for the object that you're looping through. And then in this infinite while loop, we try to get the next value through that iterator. And if there is a value, we will print the value. Okay, that's what the body of the loop is. Whoops. That's what the body of this for loop is up to, is just printing. All right. I got to get my mouse under control. There we go. Okay, so we're just going to print the value of the current object. So in this outline over here, showing what's internally going on in the for loop, down here in the else, you can just replace the print with whatever sequence of statements you would have in the equivalent for loop. Okay, so all of the statements in the for loop would go down here in the else part. But when we get to the end of the values in this iterable object that this iterator MIT is accessing, that will raise a stop iteration exception, and we will break out of the while loop to go on to whatever follows. All right, so the for loop shown in slide 10 is actually doing this equivalent while loop thing shown on slide 11 using iter and next. What that means is that if you define the iter and next functions, methods, for your class, for loops will work for your class, period. All right? All you have to do to make for loops work for your class, for your collection class, is to define iter and next appropriately, and for loops will magically work. Okay, so here we have some examples. We also need to be able to have multiple independent iterators. That is, the class that you have needs to be able to support multiple iterators stepping through the same list or through the same iterable, through the same collection, independently of each other. And this on slide 12 is illustrating that for the built-in list collection type, that does actually work. Okay, so let me do this interactively. Okay, so I'm going to create M referring to a list of values 315. All right, so M refers to 315. This is M's ID, or that's the ID of that particular list. If I say MIT1, this is M's iterator number 1. I call iter on the object M to get that iterator. Now I can create an entirely separate iterator referring or traversing through the same object M by calling iter again. And let me prove that these are different iterator objects. Okay, so each one of these things is an iterator object, and they have different IDs from each other. However, they are both iterators over M. So if I ask for the next value from the iterator M iterator 1, I get the 3. If I ask for the next value through M iterator 2, I get the 3. Now, each of these iterators is now advanced independently of each other to the next item in M. So if I ask for the next item from MIT 2, I get the 1. And if I ask for the next item from M iterator 2 again, I get the 5. All right, so M iterator 2 has now advanced through all 3 of the items in the list M. But that has not had any effect on M iterator 1. M iterator 1 is still left behind and will give me back the 1. If I try to get the next value through m iterator 2, well, there aren't any values left in the list observing it through m iterator 2, and so I get my stop iteration. However, that doesn't, as I said, have any effect on m iterator 1. M iterator 1 is now going to give me back the 5. And if I now ask for the next value through m iterator 1, I'm out of values, and so I get my stop iteration. And I will continue getting my stop iteration exception through either one of those iterators. Those iterators are in some sense used up. But it's no problem. I can just create another m iterator for m iterator 3 here. Next item through the iterator is 3. Next item through m iterator 3 is 1, 5, and then the exception. Okay, so what I'm trying to say here is that the class does not have an iterator. The class can create as many iterators as you need on the fly, and each of those iterators is going to be independent of the other iterators, even in the case where the iterators are interacting with the same underlying collection object. Okay. So here's an example. I'm going to create a class called TupList, which implements a little bit of list-like behavior, but using tuples internally to keep track of the values that are said to be in this TupList. Now, this is dumb. I mean, it's dumb to use tuples to implement lists, but the other alternative would be to use lists to implement TupLists, which would be, I think, even more confusing. So we're going to create this collection class called TupList, which will have list-like behavior, but internally we're going to store the data in each TupList object using a tuple. Here's my initialization function, dunder_init. It takes an iterator as its argument and then uses the tuple conversion/construction function to convert that iterator argument into a tuple, which we're storing in the _vals instance variable. Okay? So that's how we're going to create a TupList. Let me pull up my file that contains this code. So I'm going to do that, and then I'll get back to you. So I'm going to cut some time out here. Okay, so here on the right side, I've got my tuplist.py program file with the first part of the definition of the TupList class. And here we have the dunder_init and the dunder_stir functions being defined. Let me just copy and paste the part of the code that's shown on slide 13 into my interactive shell so that we can demonstrate what's going on with that code. All right, so here's my interactive shell. Whoops, why didn't that copy? Try again. Okay, there we go. So now I've got this first part of my class TupList defined in my interactive shell. And here's the initialization function. Now, we also want to be able to display TupLists, of course, which in turn means that we need to be able to convert TupList objects into a string representation. My string representation conversion is going to consist of the prefix TupList, that is the class name, followed by the tuple that contains the values in the list, also converted to a string. And then these two things are just going to be appended together. So let's see how this goes. I can create a TupList by saying, let me say TupList1 gets TupList, and then I'll have an iterable in here. Let me just use a list 3, 1, 5. Okay, and so there is my TupList. And if I convert TupList to a string, TL1 to a string, there's the string representation. If I call the print function implicitly invokes the stir conversion function and then displays the result. And so there is my output from the print function. Now, I could implement a whole bunch of the list facilities like append and insert and index and reverse and so forth. But rather than just writing a whole bunch of repetitive code, I'm only going to implement the append method as an example of things that we can do with lists. Since TupList is based on using a tuple for the underlying container, if I append a value to an existing TupList, what that's going to do is to modify the underscore vals instance variable to refer to a copy of itself with this new argument value appended onto the end. Okay, so val comma in parentheses is how I create a one-item tuple. Let's imagine that I do just have a tuple containing, 9, 3, 7. So here's my tuple. And if I say tuple gets tuple plus, let's say, -4, comma, a tuple is immutable. You can't change a tuple. But as we've seen, you can sort of pretend to change a tuple by actually changing the variable that refers to the tuple to a new tuple consisting of the tuple's original value with another tuple concatenated onto the end. So this changes the variable t to refer to a new tuple consisting of the original tuple that t referred to, 937, with -4 appended. And rather than typing out a separate equal sign and plus sign, I can use the plus gets. I can say t plus gets as an abbreviation for that. Whoops, I don't want the value 13. I want a tuple containing the value 13. So t plus gets the one-item tuple 13 modifies the variable t to refer to this new tuple 937 minus 413. Okay, so that is what my append function over here is doing. Let's confirm that. So here is my TupList1. And if I say TupList1.append, I can just pass a value as an argument to append. I don't need to pass a tuple, so let me pass in a -2. And if I then print TupList1, I'll see that that has had a -2 appended to it. TupList1.append 0. Now my TupList1 has had a 0 appended to it, and so on. And I could implement insert in a similar way. I could implement reverse. I could implement index. I could implement count, and on and on. Okay, so this is stuff we already knew about how to do for a class. When we define a class, we should define dunder init, we should define dunder stir, and then we should define whatever other methods make sense for interacting with this class. Here, we also want to talk about how to implement the iter and next functions so that we can traverse through a TupList object in a for loop. On slide 14, I'm showing how to implement the dunder iter and the dunder next functions for TupList. Now, for the dunder iter function, since my underlying collection type for containing the values in the TupList is a tuple, and since I know I can access individual values in a tuple using integer subscripts, sub 0, sub 1, sub 2, sub 3, and so forth, I'm going to create for myself in this dunder iter function an underscore idx underscore index instance variable to keep track of the current index for the current iterator object. All right? So I can invoke the dunder iter function over and over again. Each time I invoke it, I will get back an iterator starting out at slot sub 0, position sub 0, within the inner tuple that contains the values. I need to return some unique reference to the current iterator object that can be passed to the next function in order to obtain the next value through the iterator. And one cheap way, easy way of doing that is to just return self. Now, returning self, that is a unique ID for the current object. And if I pass self to next, next will understand, oh, okay, now I should be accessing an item within this current TupList object. Okay? There is no specific data type that this iterator returned from the iter function has to be. So it's perfectly fine to just use some unique object, some unique identifier that can be used to identify the current object that you want to invoke next on. Let me revise my TupList class to include iter and next so that we can see what's going on here. All right, so I need to copy and paste more code now. All right, so now I'm going to have init, stir, append, and also iter and next. All right, so TL1. Oh. All right, well, TL1 is a TupList object, but I want to see what TupList 1 looks like as a string. All right, so there we've printed TupList 1. And now I can say TL1IT. Maybe I should just say TLIT1. All right, so TupList iterator 1 gets TL1 dot, my mistake, I was going to say TL1 dot iter. That's not correct. I could say TL1 dot underscore iter to invoke my dunder function. But the whole point of dunder functions is so that you can use the function name as a function and pass the object in as an argument. So just to be clear, that is exactly equivalent. When I say iter TL1, that is exactly equivalent to saying TL1 dot dunder iter double underscore like that. All right, so those two statements are equivalent. And so here I got this shocking error message that I was not expecting that took me a couple of minutes to figure out what was going on. Okay, so my mistake was that previously I had defined the TupList class to just have the $init, $stir, and append methods. With those three methods defined in TupList, I then created TL1. So TL1 is actually still referring to that old definition of the TupList class. The fact that I have redefined the TupList class to include $iter and $next is not known to the TL1 object. It is still referring to the old version of that class, and consequently TL1 doesn't have an iterator function available. So what I'm going to need to do, which I have actually already done here, and which I will now flip to this this new updated screen now, what I need to do, having redefined the TupList class, including the $iter function and the $next function, I have to actually redefine TL1 to be a TupList object using this new definition of the TupList class, and now asking for TL iterator 1 to be an iterator for TL1. Now it works fine. Okay, so I had an old class definition of TupList. I created a variable using that old definition. I redefined the TupList class, but then I tried to use a facility for my old TupList variable that my old TupList variable didn't know anything about. So now I've cleaned that up, and we're ready to continue. All right. So now I can say, now that I've got my iterator for TupList 1, excuse me, I can ask for the next value from that TupList through the iterator, and the next value from the TupList through that iterator, and the next value through that iterator. And since the TupList only contains 3 values, if I try to ask for yet another value, now I get my stop iteration error. All right, but I do now have my iter function defined and my next function defined. Therefore, I claim that TupList is now an iterable type. I can simply create another TupList iterator, TupList 2, to be an iterator over TupList 1. TupList iterator 2 is an iterator over TupList 1. And I can now ask for the next value using that iterator, TupList iterator 2, TupList iterator 2, etc. More to the point, what I'm trying to do here, for convenience, the reason for iterating implementations, the reason for implementing iterables, the reason for implementing the iter function and the next function is so that my for loop will work. All right, so let me print TL1 to remind ourselves that TupList 1 contains 3, 1, and 5. Just for gags, let me append a couple of values. All right, so now when I print TupList 1, it has many more values in it, and because I have the iter function defined correctly and the next function defined correctly, poof, for loops work. For this loop variable x in the values in TupList 1, let me print x and Shazam, it works. All right? So that was our end goal, was to define the iter function and define the next function correctly so that we now have the convenience of being able to use for loops to step through the values in this TupList class. Here on slide 15 is a similar kind of example. This time I'm creating my TupList using a tuple as my iterable. Highlighting here seems to be difficult, but in this example that I did, where is it? Here we go. All right. So in this example that I did interactively, I created my TupList object, TL1, by specifying a list as the iterable from which I wanted to build that TupList. On slide 15, instead of using a list to contain the values that I want to initialize a TupList with, I'm using a tuple to provide the list of initial, or the collection of initial values. I could likewise use a set, or I could use a stir, or something like that. If I try to say, let me see, TL2 gets tup list, and I say hello world as my iterable, now I have a TupList of all of the one-character substrings from that iterable object, hello world. All right, and so on slide 15, we're showing another example of using a for loop to step through the values. And on slide 16, I'm showing the lower level raw approach of using the iter function directly to get an iterator, and the next function directly to use that iterator to get at the next available value from the TupList. In addition to for loops working, once you have created the dunder iter and dunder next functions for your class, you can use objects of your class in any context where an iterable is required. For example, here I've got my TL2 is an iterable. It's a TupList containing a sequence of one-character strings. If I wanted a set of these things, let me say set2, I can just use the set conversion function and provide TL2 as the iterable, and poof, it works. And now I have a set of all of the one-character substrings contained within TL2. Of course, the set only contains one copy of each of those strings. All right, so if you define dunder iter and dunder next correctly for your class is now treated as an iterable, and you can use it in any context where an iterable is expected, like a for loop, or a conversion to a set, a conversion to a list, a conversion to a tuple, etc., etc. Next, we're going to take a look at sequences and the idea of how to improve your class or modify your class so that your class qualifies as a sequence. The concept of sequence is not quite as clearly specified in the Python documentation as iterable is. And as Python changes over time, the concept of sequence is likely to alter somewhat. C++ has similar kinds of things where, well, I'll get into that later, I guess. I don't want to tell you ugly historical stories about C++ while we're talking about Python. In any case, let's talk about what a sequence in Python is expected to be able to do. Basically, if you have some sequence, there are three things that you're expected to be able to do with that sequence that would qualify it to be thought of as a sequence. First of all, it should have a finite length, And by that, we mean that you should be able to invoke the len function on it to find out how long that sequence is. Internally, within the definition of the class, this means you have to define a dunder-len method. Another thing that a sequence ought to be able to permit is subscripting with the square bracket notation. You should be able to index the individual items within a sequence starting from sub 0 and going up to sub whatever the length is minus 1. So if you've got 10 items in your sequence, you should be able to access them from item sub 0 up through item sub 9. Now, you may, if you want to, also implement the negative subscripts. Okay, you can implement minus 1 to be the same thing as the last item, minus 2 to be the same thing as the second to last item, etc. That is not strictly required, but what is required is that you should support forward indexes from sub 0 up to the length minus 1. You should also support, in order for your class to qualify as a sequence, the idea of slices, okay, where we have a starting position, one past the ending position, which we'll call the stop, and also a step size. And it turns out that to support both indexing and slicing, all you need to do is to define a method called dunderGetItem that takes an integer as its argument and that returns the value using that integer as a subscript. Okay, it turns out that if you just define dunderGetItem, that will support both indexing and slicing. Okay, so in order to cause the class to be treatable as an iterable, we had to define dunderIter and dunderNext. Now, to qualify as a sequence, we have to define dunderLen and dunderGetItem. So let's take a look at that. Here, once again, we're enhancing the capabilities of our TupList. For the dunderLen function for our TupList, this, it turns out, is easy to implement because we are using a tuple as the underlying collection type. And for a tuple, we already have a len function that we can call. So we can define the dunderLen function, the dunderLen method for the TupList class, by just turning around and calling len on the vals instance variable within the current TupList object. GetItem is a little trickier because the index that we pass in can be one of two different things. It can be a single integer index, like sub 0 or sub 5 or sub 47 or whatever. Or it can be a slice with a starting position, a stopping position, and also optionally a step size. So to implement GetItem, we have to differentiate between those two different types of arguments that this index could be. There's a function isInstance that's built into Python that we can call to detect whether the index that we received was some kind of slice. Okay, slice is data type, just like int or float or bool or TupList for that matter. And so we can ask, is this index that we received an instance of a slice? If so, then what we're going to do is to create a sublist using that same slice within the underlying vals tuple. All right, so creating a slice of a TupList turns out to be relatively easy because creating a slice of the underlying tuple is also relatively easy. On the other hand, if the index that was passed in is not an instance of a slice, then it must be an integer, or at least we hope that it's an integer. And so we're just going to turn around and pass that index as a subscript into the underlying tuple. Now, if this index is mistakenly a float, or if this index is out of bounds or something like that, then accessing the value associated with that index is going to result in an exception being raised. So we might get an index, an index failure or a type failure or some kind of exception like that. But assuming that the index really is just an integer index, we will get back the value in the underlying tuple. All right, so let us try that out. Now I'm going to copy my entire TupList code, including dunder init, dunder stir, append, dunder iter, dunder next, and now we're also adding dunder len and dunder get item. So TupList will now be both iterable and a sequence. Let me copy in all of that code. All right, so here's my dunder len and dunder get item code. So I have quite a bit to copy and paste. All right, here is my new and improved ultimate TupList class. There we are, and this time I will not make the mistake of trying to use the old TL1 as a sequence. So let me recreate TL1 as the new kind of TupList. And I'm going to put, well, let's see. So here I've got, well, let me do it the way it's done on slide 19. All right, so we're going to have the values in our new TupList are going to be 2, 5, 11, 9, -3, 7. And so if I print, oh, that was supposed to be TL2. It doesn't matter. It doesn't matter. No, I better, all right. I'll just create TL2 as a reference to TL1, and that will work out the same way, basically. So now I'm going to print that TL2 contains, and TL2. All right, so TL2 is a TupList containing 2, 5, 11, 9, -3, 7. Good. And I know that I can get an iterator. TupList iterator 2 is iter of TL2. So the next value from that iterator is going to be 2, and the next value from that iterator is going to be 5. But let me use this TupList as a sequence. I can access a particular item out of that sequence by saying TL2 sub 0. That will get me the initial item. Or TL2 sub, let's say 3. That will get me the 9. Okay, TL2 sub 3 gets me the 9. Luckily for me, because the underlying data structure is tuple, which I know because I wrote the TupList class, but if I'm using the TupList class, I don't know that necessarily. It turns out that negative subscripts also work for me. Well, they work if I give the correct variable name. So TL2 sub -1 is a 7, all right? So that's the last item in the TupList. If I were not fortunate enough to have some simple underlying collection type like a tuple, I would have to do some work. I, as the developer of the TupList class, would have to do some work to enable negative subscripts to work if I want them to. And let me just print TL2 again. since we're going off the top of our screen here. I can also do slicing. So I can say things like TL3 gets TL2 sub 1:4. All right, so there's a slice. And that slice is going from item sub 1 up to, but not including item sub 4. So that slice should contain 5, 11, and 9. And the slice should be of the same data type as TL2. If I print TL3, I see, sure enough, that slice is itself a TupList, and it does contain the values that I expected, 5, 11, and 9. Cool. All right. So we now know how to, given a class that contains a collection of values, we know now, we do know now how to make that class be an iterable using dunder iter and dunder next, and how to be a sequence using dunder len and dunder get item. And there we are.